Bayesian learning. And then I guess you already looked at Bayesian learning at the beginning in terms of a discrete hypothesis space. What becomes interesting is that normally the hypothesis space is continuous, and that brings up interesting headaches. So this was one of my questions on the Piazza forum. We try our best to not touch continuous quantities, and yet we stumble into them anyway, right? So we basically told ourselves that we're only looking at discrete state spaces for Markov-Radiation processes, and so fine. And there are people who look at fully observable continuous state spaces. Okay, Markov-Radiation processes can be fully observable and continuous. We made our life simple by saying fully observable discrete state spaces. Okay. However, the moment you had partial observability, we were dragged into dealing with continuous quantities, because essentially the belief space is a continuous quantity, right? And that basically the same thing happens here. In the Bayes network inference, when we looked at Bayes networks, we mostly looked at discrete variables. Okay, that's the examples that you saw. You know, the burglary, etc., earthquake, etc. They're all discrete variables. So of course you could have Bayes networks on continuous variables. We didn't discuss that. There is theory of that, and you know there are some of the inference algorithms work, some don't for the continuous quantities. But we basically avoided dealing with continuous quantities there. Okay. However, we'll see today that while from the point of view of Bayesian view of statistics, learning is nothing but inference. Learning is just inference with one extra level added. Okay. Previously, you were inferring the values of the domain variables. Now you are also making inferences on the values of the hypothesis variables, right? So far, so good. Everything is nice because you just basically are continuing to consider hypothesis the inference alone. So there is no separation between learning and inference. That's the nice part. However, the hypothesis variables most of the time wind up being continuous, even when the domain variables are discrete. You see what I'm saying? Okay. So if you only cared about discrete variable based networks, by the time you start looking at Bayesian learning techniques, Bayesian learning is nothing but inference, except now the hypothesis variable is continuous. It's very hard to motivate discrete hypothesis spaces in most cases. The candy example is a very nicely constructed example where the hypothesis only had 5 possibilities. That was a nice discrete hypothesis space. Okay. Whereas if you start talking about the probability theta that a particular coin comes heads, and I just don't know what that theta is, and every possible value of that theta is a hypothesis. So theta is a continuous variable, certainly. Okay. Even though the outcomes are heads and tails, which are discrete, but the variable itself is the hypothesis variable itself is continuous. Okay, so there are 2 things that go on in today's lecture. One, of course, is sort of revisiting. I mean, in some sense, you talked about Bayesian learning in the beginning. The 2 videos you saw, I think the first one, the candy example, was all about Bayesian learning, and then we started from there, and we said, let's just make our life simple by doing maximum, like first map. That means rather than consider all the hypotheses and considering what each of the hypotheses will say what the prediction is, and taking a weighted prediction, which is what Bayesian learning does. That's why it's not learning, it's just inference. Okay. Instead, what we said is let's just look for the one hypothesis for which that summation will be the highest, and that would be map, maximum a posteriori, right? And if that does not, and then we went further and said, well, let's not even consider the likelihood of the hypothesis. Let's just consider the likelihood of the data. Okay, and that became maximum likelihood estimations. Okay, so there was Bayesian learning, and then there's MAP, which is a huge approximation to Bayesian learning, and then MLE, which is even more huge approximation to Bayesian learning. And then we've spent our time talking about MLE until now. Okay, so now we'll go back to Bayesian learning because there actually it has several advantages, and in particular, we'll wind up looking at Bayesian learning in the context in the context of all these language models, that we'll be looking at starting next week. Okay, like LDA and so on. Okay. So the two things that you want to keep track in as the background material in this is, one, of course, is why are we going back to Bayesian learning? What's the advantages of it? And the second, of course, is how you are forced to deal with continuous variables. Okay, you're forced to deal with continuous variables, even though your domain you thought was just discrete. Okay, so there's no getting away from it. Okay. Okay, so before we go forward, actually, this is something that I feel I should do. Some of you are probably aware of this distinction between Bayesian statistics and frequentist statistics. I have probably mentioned it a couple of times, one time at least in this class, but it's kind of useful to have this. This is sort of a religious war in statistics community, and you should be aware of it. Okay, so the Bayesian learning versus frequentist learning, essentially, frequentists are the so-called classical statistics. Okay, and what they basically say is probabilities are asymptotic frequencies. If you have a probability, you cannot just make up a probability. If to say that a probability of an event is a particular number, you need to be able to essentially repeatedly sample and then take the asymptotic ratio. That would be the number. That's called the probability. Okay. Now, when there is, and then from a point of view of frequentists, there is a true hypothesis. There is a single true hypothesis. There is truth out there. Okay. And then hypothesis, because of which hypothesis is not a random variable. Because hypothesis is not a random variable, you can't put a prior on it. You can't use hypothesis the way all other. So, for example, I cannot just say probability of hypothesis because that makes it look as if hypothesis is a random variable. Okay. I also cannot say PD given H or PH given D. All of these frequentists will basically get really mad at you if you try to do that. Okay. So instead, what they would say is, so basically, hypothesis is not at all a random variable, and so you cannot put priors on it. And the way you try to learn from the data, so having a prior from a frequentist point of view, having a prior on the hypothesis is sort of like cheating. It's basically you are saying that I know something more about the problem than what the data is telling me. Okay. That's one. That's basically the frequentist side. The Bayesians, essentially, the difference comes here itself. For a Bayesian, a probability is just a degree of belief. Probabilities don't have to have any connection to asymptotic ratios. This turns out to be a very huge distinction. Okay. For example, if I ask you the following question, probability that Einstein drank a cup of tea at 4:13 p.m. on February 26, 1920. What is it? 0.5. So this guy is who? He's a Bayesian. Right? Basically, he just gave a number, and this is not a repeatable experiment. This is not a repeatable experiment. Okay, so frequentists basically say, what the heck are you asking me? There is no number for, there is no probability for this. You cannot talk about probabilities for this. To the extent you feel comfortable giving a probability for this, you are a Bayesian. You get my point, okay? So Bayesians essentially think that it's not my job to question where you came up with your degrees of belief. Then you might think, hey, if you can come up with any random degree of belief, then what is statistics doing for me? Okay, all probability and statistics is going to do is to hold you accountable for your degrees of belief. If you, for example, thought that the probability that Einstein was drinking a cup of tea at 4:30 p.m. on February 26, 1920 to be 0.9, okay, and then did something, came to another conclusion which sort of would not make sense if somebody was drinking tea. So, for example, when he was drinking tea, then suppose I also asked you what's the probability that he was at the same time drinking coffee, and if you also said that's 0.9, then your degrees of beliefs are inconsistent. You can't both be drinking coffee and tea, although I guess, but you know, let's assume that to the extent you can only do one at a time, then your degrees of belief are inconsistent. So Bayesians only care about making sure that your degrees of belief are consistent. If you did some additional due diligence and got this number, fine. If not, that's fine too. You can start with any numbers, and then I'll make sure that I make you, I'll hold you to those numbers. Which is why, by the way, in the Bayes networks, those numbers that we put in, you can put any numbers there. And I said that will give you a consistent probability distribution. But given that distribution, then I can infer, if you say the following is the evidence, I can tell you what is the posterior and some of the other variables. Okay, so this is a big difference that you want to keep in mind between Bayesian versus frequentist view. So a Bayesian might say, like, I believe it's 0.4. Why do you believe so? I don't. Why do you need to know? I believe it's 0.4. Okay, and then frequentists will say, can't say. It's not a repeatable experiment. See what I'm saying? So one more thing, of course, is so for once I have this, the other thing that Bayesians do, which we take for granted, okay, is hypothesis is just a random variable, because of which you can stack data and hypothesis into the same network. Right? In fact, we'll see in a minute that in the new Bayes networks that we'll be looking at, hypothesis would be a variable that would be causing the data. I mean, that basically, there will be like an arrow from the hypothesis variable to the data variable. You see what I'm saying? So that means the same exact network has both hypothesis as a variable and the data variables as variables. Everything is variables. Everything is random variables. So I can condition with respect to variables given other variables. I can condition with respect to hypothesis given other variables. I can condition with respect to variables given hypothesis. Wherever I can put a random variable, I can now put a hypothesis. Okay, so we were doing this, right? When you did the candy example, you did this. To some extent, a classical statistician would throw you out of the class if you try this kind of nonsense, because hypothesis is not a random variable. Okay, now, so then the hypothesis prior, because hypothesis is a random variable, I can put a prior on it. If it's a random variable, I can put distributions on it. Okay, so hypothesis is a prior. So one of the interesting things that Bayesians do is they'll put a prior on anything, because everything is a random variable for them. Okay, hypothesis is a random variable. Okay, so one of the interesting things we'll see is the infinite regress doesn't have to stop. I'll say something and then hopefully it'll come back to you when we look at LDA, that you can have distributions at several levels. You can have, so for example, the beta distribution that we mentioned last class, which we'll be again mentioning today, starts with hyperparameters, alpha and beta. And it turns out that, and beta distribution is actually constraining the theta variable, which is the hypothesis variable. Now the alpha and beta are also parameters. You can call them hyperparameters. And some, Bayesians would put a prior on alpha and beta. You see what I'm saying? For weird reasons, I'm not a big pop music fan, but for some weird reasons, I keep getting reminded of some Beyonce song about put a ring on finger, So Bayesians will put a prior on everything. Okay? So, because for them it's just a random variable. It's a huge difference, it's a distinction that has humongous semantic import. Okay, large numbers of religious battles were waged in statistics departments. At one point of time in statistics department, if you say you're Bayesian, they'll just throw you out. Okay, even now, I think, now actually it's sort of opposite. There's more, I think, Bayesian statisticians in the statistics departments. Okay, so, you know, the other thing is, actually this is kind of cute. So God doesn't play dice with the universe. Does anybody know this? Einstein. So is Einstein Bayesian or frequentist? The reason God doesn't play dice with the universe was because people are trying to come up with hypotheses. Science is coming up with hypotheses as to how the real world works, right? So they were trying to come up with hypotheses. Quantum physics was a hypothesis. And basically, irrespective of whether or not quantum physics was consistent with the observed data, Einstein said, no, I don't think quantum physics makes sense because God, I happen to talk to God every other day and he doesn't play dice. Okay, and then of course there is a rejoinder to that. Niels Bohr told Einstein, stop telling God what to do. Okay, I don't know if you guys heard that, but these two to me are essentially talking about putting priors on the hypothesis. Okay, classical statistics people will say, I would not have any prior on the hypothesis, I'll only look at the data, whatever it is. Okay. Now the interesting thing is, now if this kind of religious war has been going on for such a long time, then how come there is any statistical inference at all anyway? It turns out there is one little place where both the camps agree, but they come to the same point for different reasons. Okay, so Bayesians start with Bayesian learning and then say it's too hard to do, let's do map. That too is too hard to do, let's do MLE. By the time you came to MLE, you know that you're doing the wrong thing, but that's what you're doing right now. Now it turns out what Bayesian does reluctantly, Frequentist says that's the right thing. Finally, you came to your senses. You got rid of the hypothesis, you got rid of the prior on the hypothesis. So we now both can talk the same language. Do you understand what I'm saying? So maximum likelihood estimation based inference is common. That theory is common between frequentist and Bayesian statistics. The only difference basically is that, so Bayesians think that MLE is just stripped down special case of Bayesian learning that makes sense for large data. Because large data case, essentially, the likelihood of the data, remember there was this sum in that, you started with map, and in the sum, the likelihood of the data plus the likelihood of the hypothesis. As the data keeps increasing, the data likelihood part dominates. Okay, so even a very unlikely hypothesis will have to be taken into consideration if there is a lot of data that is consistent with it. You see what I'm saying? So in essence, Bayesians think MLE would make sense for large data. It's just an approximation that holds for the large data. And frequentists will agree with them in a different way. They say, good that you essentially got out of your hypothesis being a random variable nonsense. It's never a random variable. Just all along, until now, everything was fine except just avoid doing this kind of notation. If d given h doesn't make sense. To write d given h has to be a random variable. Syntactically. Okay? So we'll make up a new notation called b, probability d semicolon h. Okay? To say that h is not a random variable. You do this, then we are fine. You can do, both of us will do, derivatives, partial derivatives, both of them as will equate to 0, both of us will solve for the maximum of the likelihood. It's just that you would keep thinking that it's d given h, and I'll keep thinking it is probability of d under the hypothesis. Okay, so that's something to keep in mind, that essentially frequentists and Bayesians agreed completely as far as MLE is concerned. So even though they have religious differences, as far as MLE is concerned, they agree. From now, they will disagree, because now we'll actually go back to Bayesian learning. So remember that Bayesians came here rather than, basically saying we really would like to do the right thing, but it's too costly, let's just do the wrong thing for a while. For the large data case, the wrong thing would make sense. Okay, so when we go back to doing the right thing, then Bayesian learning differs quite significantly from frequentist learning. This is kind of useful to know because, in fact, some of the ideas that work across both the religions, I mean, again, this is almost a religious thing. I mean, just like, I guess, Christianity and Islam have some commonalities. They would agree on certain things, for example. I think they agree on Abraham, for example, something. I mean, I'm neither a Christian nor a Muslim, so I don't really know what I'm talking about. But they'll agree on certain things, but they will provide different interpretations of both of them. Okay, so in this particular case, they both agree on computing the likelihood of the data, and then as a parameterized expression, and finding the values of the parameters where that expression becomes maximum. That they agree. And they also agree that sometimes that kind of a maximization can be quite painful if, in fact, you have missing data case. If you have a missing data case, then essentially you would have to do EM, right? Okay, it turns out the EM procedure was actually developed by people who mostly thought they were doing classical statistics. They were doing frequentist statistics. Okay, but it's just as useful for Bayesians thinking that they're doing the wrong thing for computational expediency. Okay, so that's something to keep back in the mind while we go forward. And I'm just going to skip over this. Actually, this issue of whether or not you should believe that there is any point for prior knowledge. I think statisticians may have various takes on that, but AI people have no question. Not having prior knowledge means not having any background knowledge. All you see is the data. That's clearly not the case. In fact, many times, just with a few data points, you're able to reach conclusions because you have significant amount of prior knowledge about the world. You see what I'm saying? And so we, from AI side, the prior distributions are just a particular way of representing prior knowledge. In fact, they are not the most flexible way, it turns out. Because, in fact, you would like to write prior knowledge in logical form, maybe. Okay? But Bayesian learning actually makes a lot of sense from a, AI point of view because we do believe in prior knowledge. Okay? Okay, so now coming back to Bayesian learning, so the question is, MLE is working, everybody is using it, why do we care? Why do you want to stop it? Why do we want to learn Bayesian learning again? The reason, of course, is that MLE approximation holds only in the large data scenario, where in fact that data likelihood more than swamped the PH scenario, the likelihood of the hypothesis. Okay, and in that case, of course, ignoring likelihood of hypothesis doesn't really affect. You'll come to the same conclusion. Do you see what I'm saying? But in many other cases, in fact, it turns out that you would like to take both pieces into account. Okay, and furthermore, actually, in fact, you would not even want to make up your mind as to which is the true hypothesis. You may want to keep track of all the hypotheses. Now, here is an interesting point that I actually brought up on the piazza. So there is Bayesian learning, there is MAP, there is MLE, right? MLE is just optimizing PD given H. A map is optimizing PD given H plus PH, in terms of logs, okay? And then Bayesian learning is not picking any single hypothesis. It's keeping all the hypotheses around. And it's keeping the entire distribution of the hypothesis. What happens in Bayesian learning is the moment you see the data, so you start with a prior distribution over the hypothesis. The moment you see the data, you get a new posterior distribution on the hypothesis. With respect to that posterior distribution, you would then make the data prediction for the next data point. As new data keeps coming, so you start with P of H, but after seeing up to D10, let's say D1 up to D10, you then compute probability of h given d1 to d10. That's the posterior. You use that posterior to then predict the next data point. You see what I'm saying? And then, so you never actually pick who is the winner. You keep all of them. It may well be that some of them are clearly winners, some of them are clearly losers, but Bayesians never have, Bayesian learning, strict Bayesian learning never has to pick a hypothesis at all. Now that is actually an interesting question, whether or not human learning is that way. I don't know whether I can make a comment on that. I mean, whether I can make a guarantee on that. So that was where my point in the discussion on the answer came from. So in general, humans tend to go with like one winning hypothesis. Because otherwise, in essence, remember that what we are calling hypothesis here, if you get this hypothesis and that sort of seems to hold because of the large amount of data, that becomes part of your knowledge now. And then you build on top of that knowledge. You see what I'm saying? Now, if at each level you never actually prune any hypothesis, you keep track of all possible hypotheses, then essentially the knowledge base can be quite complex. You never actually make up your mind as to what you learned. It's not lossy, but it's just the inference on such a knowledge base could be extremely complex. Okay, so this is basically what I was saying. Even saying, that it's either a man or a woman is harder than just going with one possibility in terms of inference, not surprisingly, because disjunction is harder than conjunction in inference. Okay, this is something where Bayesian learning, so the map case is easy to argue from human learning point of view, because humans do have prior ideas as to what kinds of hypotheses are more likely, what kinds of hypotheses are less likely. And just because the data is consistent with an unlikely hypothesis, they may not just jump with that. But the pure Bayesian learning, it's harder to make sense of it from cognitive perspective, because it's not very clear that we actually keep this, the entire set of hypotheses without ever committing to one. But when we're doing Bayesian learning, that's what we do. We actually keep the entire set of hypotheses because we have a posterior. We have a prior on that, and then we compute posterior. Okay, it's something that we will just basically use it as like a building block as we go forward, but you have to keep in mind that Bayesian learning, there is no learning in it, right? Which means you never make up your mind. It's totally least committed. I never will make up my mind. If the new data comes, so a Bayesian never changes their mind. Like you cannot ever say Bayesian is a flip-flopper. Remember in politics, that's like a big deal, right? So you see some data and then you come to a hypothesis, and then if you see more data, if that you come to a different hypothesis, people can call you're a flip-flopper, right? Kerry obviously would have avoided this problem if he said, I'm just doing Bayesian learning. I'll never make up my mind as to what the real hypothesis is. This is 0.7785, this is 1 minus 0.7785. And then you show me more data, I will change the 14th decimal place of these two guys, and you cannot accuse me of changing my mind because I never made up my mind. Okay, as silly as this discussion might seem, that's the true import of Bayesian learning not being learning. It's just inference. You keep track of all possible hypotheses. Okay. Now, in the question, of course, so making all that, having made all that, prior thing, the question, of course, is if you want to do this, but then technically, what are the hurdles? Okay, we did do this for the discrete hypothesis case. Okay, okay, so anyway, this is the example. This one is basically just showing one more repetition of the point that when you do have prior knowledge, MLE doesn't really allow you to use it, whereas Bayesian learning would allow you to use it. That's the point. So the question, of course, is how do you do? What are the technical issues in doing this? We did one example for the candy case, which is very simple. Now I'm going to do an example for basically coin toss case. Okay. Interestingly, the coin toss case turns out to be more difficult because in the case of coin toss, the probability that the coin comes heads is theta, or theta is a real variable. And if you want to put a prior on it, you need to put a real distribution on theta. Okay, so let theta be, so this is just the Bayesian way of doing coin toss. You saw a coin is being tossed in front of you, and you see, let's say, 15 tosses, and you see whether they came heads or tails, etc. And now you're about to predict whether the next one will come heads or tails. That's what you're trying to do. That's what all the point of learning is, right? We start with the obvious thing that we'll have a theta with a probability that the coin comes heads, and then each different value of theta is a different hypothesis. That means there are infinite number of hypotheses. Okay, and then let pH be the hypothesis prior. The question, of course, is how do you specify this prior? Okay, now if you do have the pH, okay, p theta, then we can always compute the posterior after seeing the data as actually this is in terms of, so p theta given d is is proportional to p theta given theta times p theta. No, I wrote hi here, but h basically for us hypothesis is theta. That the value of theta is the hypothesis. Okay. So you can compute the posterior of a hypothesis given data, which is like the significant step in any Bayesian learning. Okay, as you see data, you compute the posterior of the hypothesis, and then once you know the posterior of the hypothesis, if you want to predict the next data, then you do a weighted, prediction. Okay, so you can compute it this way. So the only question, so this looks great. What's hard about this? What is hard about this is, suppose, since theta is a continuous variable, you need some parameterized representation. There is no way you can represent this distribution extensionally. Okay, so it's out of question. You can never represent this distribution extensionally. So you need a parameterized representation of p theta. Let's suppose, you pick some known distribution, let's say binomial distribution, let's say Poisson distribution, and then let's say you have this information, so you multiply p theta times p d theta, b d given theta. Now the question is, would the new distributions, what shape would it have? And how many parameters would be needed to represent that new distribution? Do you understand what I'm saying? Now we are no longer talking about whether Bayesian learning is good or bad. We sort of made all this argument that let's do it now. The question is, if you want to do it, you need to have some technically feasible way of keeping track of p theta given d given p theta and p d given theta. Right? So the thing that can happen if you're not careful is, even if you have a compact representation for p theta, okay, imagine, let's say you kind of put some sort of a nice unimodal distribution for p theta. Okay, after this update, it might become like this. So it's more than likely that now this distribution will require more parameters. A unimodal distribution, for example, might, you can represent it as something like a normal distribution, let's say. So you have multimodal distribution, you need more parameters. Then after some more update, it becomes like this. After some more update, it becomes like that. Okay. The question is, I'm not questioning, is that a reasonable belief on the posterior of the hypothesis? I'm questioning, do I want to represent this exactly using some parameterized distribution? If so, then my number of parameters might increase exponentially as data keeps coming in. Do you see what I'm saying? So this sort of makes, in some sense it's saying, don't show me any more data because I will learn too much and it won't fit in my head. Right? Because my posterior, for Bayesians, fitting the learning in head is keeping a representation of the posterior of the hypothesis given the data. Okay? And if you essentially have arbitrarily shaped posteriors, they might take a large number of parameters to represent. I'm not saying is that the right thing or not. I'm saying, do I have the I mean, am I eager enough to represent it in all its glory? Instead, suppose I were to tell you that, notice the thing that is of these two, of this and this, which of them is problem specific and which of them you can choose yourself? P d given theta is problem specific. It's about that, once you pick the hypothesis, the probability of the data given that hypothesis is about that problem. You agree? Okay, so this is a distribution too, but this distribution comes from the problem. So you don't get to choose this. What you have a choice on is choosing this. Now, actually, you don't really have a choice on this either, because you might actually have a very specific distribution that you happen to know is true for theta, okay, and which, if you actually multiply it by the known PD given theta, eventually it becomes like this, and you die in terms of representing it. But suppose you were to take the stance that, okay, I know a lot about this problem, but I'm not unhappy to represent my prior knowledge in a form that somehow flows well with the given form of this, so that when I multiply this by this, what I get here would be in the same form as this. Did you understand what I just said? Okay, so all I want is, given the likelihood, which is problem dependent, pick a prior distribution such that that prior times likelihood will have the same format as the prior. If you do this, that basically, such a prior is called a conjugate prior. I'm sorry. Such a prior is called a conjugate prior. Okay, so this is roundabout argument as to why conjugate priors are important. I hope you get this. Okay, it's worth getting it. Okay, really, you have. It's not that you have any choice on this. If you really want to represent your prior knowledge about theta in excruciatingly exact form, there may never be a conjugate, a particular distribution of the conjugate prior form that is a close enough approximation. So you would not be using that. But you're saying, let's just fit one of the conjugate priors to my prior knowledge, because then I will multiply this by likelihood, I will still be in the conjugate prior form. That would avoid this problem of the number of parameters for representing the distribution increasing with the data. Now here's my question. Why did we not have to deal with this when we talked about candies? Why is this not a problem at all? Why am I making such a big deal about conjugate distribution now, but we didn't say anything about this when we talked about candies? No, it wasn't one hypothesis. It was discrete, fine. So that's not the point. It was a discrete hypothesis, I agree. Why didn't we think of conjugate hypothesis there? Conjugate priors there. Why wasn't it important? If we didn't think about, remember, the reason we're thinking about conjugates here is because the boogeyman is, if you don't think about conjugate hypothesis, conjugate prior, then the posterior will become arbitrarily larger in terms of the number of parameters you need to represent it. Okay? Keep that in mind. Now tell me, why didn't we care about this in the context of candies? So the guy who's already in the water, what's the point in talking about I'm feeling cold, right? How did you represent the prior for the hypothesis in the candy example? You represent it in a tabular form. How can the table become any larger? That is the most extensional way. For every value of the hypothesis, you have a probability. If you represent it that way, it will never increase any more than that because you're already sunk. Do you guys understand this? Okay? If I give you, so it's the issue of discrete versus continuous hypothesis is different from the issue of parameterized versus extensional representations of distributions. For continuous parameters, continuous variables, you don't even think about extensional representations. But for discrete variables, you can have both parameterized and extensional representations. If it's a discrete variable with many, many values, you would go with parameterized representations. Poisson distribution is a parameterized distribution. Okay, so the real reason why we did not have to think about conjugates there is because we were not representing the distribution in a parameterized form. We are representing it in full extensional form. And once you represent it in full extensional form, it will just remain the same size. What?
The data will get incorporated.
Yes, basically the distribution, you are representing it with as, if you have 29 billion values, 29 billion discrete values for this variable, how many numbers would you need to represent the distribution? Maximum 29 billion minus 1. That's it. And you start with that and you update, you get another 29 billion minus 1, update 29 billion minus 1, update 29 billion minus 1. So if you are not dead there, you will continue to live here. But most of you will be dead in the first place itself. Okay, this is a rich world. Here you actually have a way of representing the 29 billion distribution as a parameterized distribution which has only a couple of parameters. In that case, then you can say, oh, I started with so few parameters, my number of parameters are increasing. I don't like it. Then I want to talk about conjugate distribution. Okay? Okay, so now the conjugate distribution so now P d given theta is what for pointers? It's a binomial distribution, right? What's the probability that you will get heads given that the head probability is P, and head probability is theta? And what's the probability that you will get tails given that the tail probability is theta? Or what's the probability that you will get 2 heads and 3 tails given that the head probability is theta? That's theta squared times 1 minus theta cube, 1 minus theta whole cube, right? What is that distribution? That's binomial distribution. And the conjugate for binomial distribution turns out to be the beta distribution that we talked about a little last time. And the point is that if you multiply this distribution, okay, so the beta distribution looks like this. And you will multiply, after that, if you saw, let's say, h heads and t tails, so then you will multiply this into theta power h and 1 minus theta power t. Right? When you multiply, this will just be written as theta times a plus h minus 1 and 1 minus theta times b plus t minus 1. But that just is another beta distribution. It's just the hyperparameters a plus h and b plus t as against a and b. You know what I'm saying? That is the thing. Again, the reason I'm going through this is if you have a lot of background in statistics and conjugate priors, this could be boring to you. For most CS undergrads, they don't necessarily have it. And for those, it would be very useful to know why you're doing this. Okay. So this conjugate distribution has this property that, of course, it will keep its form. Once it keeps its form, then I won't have this problem. However much the data is, the parameters will still be just 2 parameters. Alpha and beta. Challenges increase. Okay. So that's the reason why. So now this is sort of a convoluted reason. You have to understand this is a convoluted reason. This is like a second order version of Grant looking for last case under the light. Not the first order, but the second order version. Okay. Now the drunk is saying, I know a lot about what the prior on the theta is. If I really want to represent it, it's not. There's not going to be any good beta distribution that is a good, approximation. So, for example, let's say this drug happens to know that this particular thing. I know this drug happens to know that. So I'm about to task points. You happen to know that you have seen me as an unfair guy, and you know that I don't have a 0.5 coin at all. But you also seen me buying two types of coins somewhere in the market. One coin with a 0.3 and one coin with a 0.7 hedge probability. You see what I'm saying? So how do you represent your prior on theta? Your representation of the prior on theta would have to be like that. A peak at a 0.3 and a peak at a 0.7. There is no good approximation of a bimodal distribution like that with a beta distribution, because if you look at next page is the beta distribution. These are all the things I just already said. This is beta distribution. This is how it looks for different values of alpha and beta, how the beta distribution looks. So this is just directly from the Wikipedia page. Okay. So you could see that last time I was singing praises of the beta distribution. Notice that I can have this kind of prior knowledge, that kind of prior knowledge, that other kind, that other kind. Isn't that so nice? But what if I have prior knowledge which is bimodal? Which of these is a good approximation? None. If you have a line finding software and you give it a parabola, does it say, sorry, there is no line here? It will find one. If you give it a circle, it will still find a line. It's just that the best fit line would still be quite far away from the data. Similarly, once you decide to go with the beta distribution, your best fit beta distribution parameters to represent the prior knowledge you have may well be quite far from satisfactory. This is why I'm saying this is a second order drunk example. So all you can see is you can pick any one of these. There are infinite number of these. You can pick any one of these. Pick the one that's closest to you. Well, that's great. If in fact my knowledge is mostly unimodal. It's not so great if my knowledge is multimodal. Okay, so that is, you don't get mathematical ease without sacrificing something else. You got mathematical ease, but you sacrificed the ability to represent your prior knowledge. So in this particular case, even though you knew that I am between I'm either 0.3 or 0.7, that I have specifically either a 0.3 or a 0.7, coin, you have to still pick one of these guys. Okay. Fine. So anyway, so once now we decided that beta, and the reason we went with beta, remember, is because it has a nice property that you multiply beta by binomial, you get beta back. Okay. Now, one other minor thing to talk about before we go forward is, the binomial distribution, not surprisingly, is for variables of two values. Okay, and there is a distribution called multinomial distribution. A multinomial distribution would be distribution for variables with n values. So, for example, the distribution of distribution over a dice, a 6-faced dice, it would be a multinomial distribution. Okay, so how would that look? It would basically look theta 1, theta 2, theta 3, theta 4, theta 5, and then 1 minus, and you can also write theta 6, okay, such that all these numbers together will add up to 1. right? For every dice, you need 6 numbers to represent its, how fair that dice is. Right? Now, if you want, just like you had prior knowledge on my coin, if you wanted to express your prior knowledge on my dice, then you need a prior knowledge, you need a version of beta distribution that generalizes to n dimensions. Okay? So there you would just need essentially a beta distribution, some kind of a beta distribution, I'll call it beta for now, on alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Okay? And that would just have the property theta 1 for alpha 1, theta 2 for alpha 2, theta 3 for alpha 3, so on. Okay? This distribution, the generalization of the beta distribution to multinomial case, is called the Dirichlet distribution. Okay? Beta distribution can be seen like this in 2 dimensions. Dirichlet distribution is very much similar. Okay, in the sense that Dirichlet distribution cannot represent multimodal prior knowledge. If you have multimodal prior knowledge, well. In general, statisticians don't like multimodal anything. Okay. By the way, this whole thing about conjugate distributions and the number of parameters not increasing is very closely connected to why Kalman filters are such a big deal. Kalman filters essentially have the same sort of, what we are doing here is you have a hypothesis and you multiply the data likelihood to get the posterior on the hypothesis. Okay, in the Kalman filtering, you have an estimate of where you are, you look at the observation and you get a new estimate of where you are, posterior on the estimation. Okay, so Kalman filtering is like Bayesian learning. It's just that you are basically maintaining there the posterior on your state. Here you are maintaining the posterior on your hypothesis. For the same reason, if the PO given S, which is the observation given state probability, if it can be written as a, if it's written as a Gaussian, then, and if the original state distribution is a Gaussian, Gaussian times Gaussian is again a Gaussian. That's the good reason. So the state distribution, your knowledge about where you are will always be expressible as a Gaussian. Okay, and it turns out that the reason Kalman filtering fails and why people talk about lots of other kinds of filtering, such as particle filtering, is because most of the time, in many a case, you don't actually have initial state distribution to be Gaussian at all. You think I'm either here or here, bimodal distribution. So there is no actual single Gaussian. So then, of course, there are people who talked about extended Kalman filtering, etc., etc., etc. And finally, there's no way of getting away from having to deal with these guys. If you really want to deal with nonlinear, if you really want to deal with any arbitrary state distribution in the beginning, and you want to use it rather than just close my eyes and I know that I could be either here or here, let's just assume that I'm sort of like this. I'll put one normal distribution on top, right? That's the same thing I'm doing here too. Even though I know Rao either has a 0.3 coin or a 0.7 coin, I'll put one beta distribution which is sort of a unimodal one, which is close enough to this. You lose something. What you lose in the learning case is the efficiency of learning. You need more examples to come to the same accuracy. What you lose in the filtering case is the efficiency of predicting exactly where you are. Do you see what I'm saying? Okay. So eventually, these conjugate filters, conjugate distributions are essentially kind of, they'll help you along because it makes, mathematically the problem tractable. But eventually, if you want efficiency, you need to keep the problem as it is and develop approximation techniques. And that's what happens, for example, in particle filters. Okay. But anyway, so in the case of Dirichlet distribution, it turns out Dirichlet distribution has the same exact kinds of problems as beta distribution, and same exact kind of pluses and minuses that the beta distribution has. Okay? Okay, so if you happen to have some prior knowledge, then you can put it. Now, one thing that basically, if on one hand, if you're not particularly good at saying, so here's the thing, earlier I said, I think Rao, that you may know that Rao has a 0.3 or a 0.7 point. Then you may want to represent it, you will be unhappy about how to represent this. Suppose you didn't know anything about what kind of a coin Rao has. You have no idea. Can beta distribution be fine for you? Did you understand what I just said? You have no idea what kind of a coin I have. It can be a 0.3 coin, 0.7 coin, 0.5 coin, 0.6699887 coin. Yes?
You said you could generate some form of something similar to IID.
No, it's not IID, uniform. Basically, you can get a uniform distribution. And beta distribution, one version, basically can get you close enough to uniform distribution. So, people who have no prior knowledge would be happy with either this or this shape. Okay, the two things. One is that prior is allowing you to represent your prior knowledge, and then secondly, if you represent your prior knowledge at all in some parametric form, Bayesian learning will allow you not to have to prematurely make up your mind. So in the case where you did not know what kind of coin I'm holding, you pick a beta prior that corresponds to something close to uniform. And then as the data comes, you are becoming more and more close to what the data is saying is the posterior distribution on the hypothesis. You still don't have to pick a single hypothesis. You are able to essentially provide automatic regularization. By picking a single hypothesis when, with very little data, you get overfitting. Okay. Whereas Bayesian learning, nobody talks about overfitting at all. This is another very interesting thing. For those of you who come from machine learning, there is no overfitting in Bayesian learning. I'm not making up my mind. How can I be overfitting? You see? Okay, so that's basically about the beta distributions, and then when we look at LDA, we will look at. So in the case of LDA, so in the case of this, basically this is a 6-phase dice. Okay, think of the following thing, just a slight change of pace. Think of the following thing. I have a bunch of, I'm trying to make a sentence of k words. I'm trying to make a sentence of k words. I have a vocabulary of v words. How do I make a sentence? Forget about grammar and everything else. Okay? To make sentence, I have to pick a word, put it here, pick a word, put it here, pick a word, put it here, with replacement. The only thing that I have is what probability do I pick a word? I argue that this V is a V-sided dice. It's a V-sided dice. And I'm flipping that V-sided dice, whichever word it comes up with, I'm putting that word in the first place. Then again flip it, and whichever word it comes, I put it in the second place, third place, fourth place, etc. Now I already have a k places. Now I have a sentence. I generated a sentence. It's a language model. Okay. Now, if I have a question like this, and I'm sort of, jumping ahead to 2 weeks, not next class, but the week after, next class. Okay. Now, if this is the way I think you are generating sentences, and you show me some sentences you have that generated, then my learning problem would be figuring out the probabilities for the dice, the word probabilities. So language learning is finding the dice probabilities. Right? Except it's not a two-sided coin, it's a V-sided dice. So to provide a prior on the V-sided dice probabilities, I need a Dirichlet distribution of size V. That's what we would be doing next week. That's the connection. Okay, fine. Anyway, so a few, before we leave for today, let's have a few quick mathematical properties. Although you should just do it yourself, you have to remember your integration and you have to know about gamma functions and so on. This is a neat way to remember your background in almost this is single variable calculus actually. Okay, so it basically I told you that a beta function, a beta distribution is of the property is of the form x power alpha minus 1 times 1 minus x power beta minus 1, where alpha and beta are real numbers. Okay, now the question of course is to make it a distribution, what do I need to do? I need to divide it by the area under the curve, right? Because this is a continuous, x is a continuous value. So if you actually just draw this, you'll get one of these curves. Depending on the alpha and beta values, I'll get different kinds of curves. And in fact, these curves have the properties that if alpha plus beta is a large number, then the curve would have a very sharp peak. Okay, alpha plus beta tells you how peaked the distribution is going to be. This is true for the Dirichlet too. So it says alpha 1 plus alpha 2 etc. plus alpha n is a large number. Dirichlet would be a peaked distribution. Okay, and then if alpha, in this case, if alpha, then there are only two things here. So if alpha is greater than b, then the mode is towards 1, and if alpha is less than b, the mode is towards 0. Mode means the peak. Okay, and then finally, if alpha plus b is greater than 1, it will be convex upwards. If alpha plus b is less than 1, it is convex downwards. These are all just mathematical properties. You just plug it in and you draw this curve, that's what you see. So the only question, of course, is without knowing what the specific alpha beta values are, because this can be any of these curves, do I have a general expression for the area under the curve? This is where background in calculus will be helpful, because what you need to do is evaluate that integral. You need to evaluate that integral from 0 to 1 u power alpha minus 1, 1 minus u power beta minus 1 du. Just evaluate that integral. Okay, now it turns out that this integral essentially can be written in terms of another integral called gamma function. Okay, so basically this integral can be written as gamma of alpha times gamma of beta by gamma of alpha plus beta. So it's a gamma function. Now what is a gamma function? That's a gamma function. Okay, so gamma function basically is 0 to infinity e power minus t, e power minus t, t power, e power minus t power z minus 1d. Okay, this turns out to have, this basically, it's a function. Nobody actually has closed form solution for this integral. It's a very useful integral. It has beautiful properties. So for example, one of the interesting things you can do is if I can evaluate gamma of z plus 1 and show that gamma of z plus 1 would be z times gamma of z. Okay, now if you see this, you should realize that it has this sort of a factorial nature to gamma. So n plus 1 factorial is n times n factorial. Okay, in particular for integral values of z, okay, gamma n is nothing but n minus 1 factorial. Okay, and there's beautiful theory behind gamma functions as to, so gamma, basically you have factorial function. A factorial function is only defined for positive integers. It's not defined anywhere else. And one issue is, can you essentially define an analytic continuation of this function that has good properties? Okay, now of course, if I tell you here are some functions, here's a function with values at the integers, what are the various ways you can complete it? Well, I can do it. That's a function. Okay, there are many functions I can do. Okay, the one that the gamma function essentially turns out to have lots lots of good properties. It's a nice continuous function, and basically it is the closest continuous function that has the properties of factorial function. Okay, and one other thing is it goes to infinity at every negative integer. This is basically the way the gamma function looks, by the way. Okay, and it goes to infinity at every negative integer, and the rest of the places it is defined and it's at times. Now, if you know the gamma function, then all I'm saying is the area under the curve of a beta distribution can be represented in terms of gamma function. Now, since gamma function is such a good function and everybody loves it so much, essentially there are obviously you can, in the old days there are tables. Now, of course, you have just you can compute the values for gamma at any point. Okay, and so even though you can't write it as a single number, this is, as far as you're concerned, it's a constant. Okay, and this constant times this will have the property that if you then integrate it, the overall thing will integrate to 1 because I just divided it by the area. So that's the deal with beta distribution. Now, when you go to Dirichlet distribution, it would have the exact same structure. Instead of alpha plus beta by alpha and beta, it will be gamma of alpha 1 plus alpha 2 plus etc. up to alpha n by gamma of alpha 1, gamma of alpha 2, gamma of alpha 3, etc. Okay. Now, what I did not show you is why this holds true, because to show that why this holds true, you need to essentially remember how to do. You cannot actually do this integration. There is no closed form solution to this integration, but you should be able to prove these, for example, by doing integration by parts. How many of you have done integration by parts in the last week? No? It's a good time to do it. Right? Okay. So then you get to do beta gamma function. I mean, you can just say, oh, those people know what their numbers are. They know, and I'm just a mediator. But if you want to at least do it once, you can do it. This is the most useful thing to try and do. This is a very useful property of gamma function. If you look at the Wikipedia page, they have like a whole slew of properties of the gamma functions. And people love gamma functions in that. Okay, it's sort of like a pie of the functions. Okay, I mean it's an ugly-looking function. All right, this is the function. It's how it looks, but it's a nice function. It has very nice properties. Okay, so one last thing before we go forward. So conjugate priors, we talked about conjugate for binomial, which is beta. For multinomial, it is Dirichlet, and for Gaussian, it is either Gaussian or normal Wishart distribution. Okay, so basically, anytime you want to compute prior times likelihood and want to get the same parametric form as the original prior, you need conjugate prior. Okay, but if you really understood this today's class, you should understand that conjugate prior is sort of fitting your prior knowledge to some reasonable line. This conjugate prior is providing you the right lines, that the right set of hypotheses, for your prior knowledge. And you pick the one that best fits. Okay, and then once you do that, essentially you get to update your posterior on the you started with the prior and the posterior would be in the same form. Okay, and then one last thing I should probably show before we go forward. Let me see. Oh, this is actually is the Bayesian prediction. So if I have a posterior on the hypothesis, then I need to predict what happens next. Okay, so this is basically what you do. So if I tell you currently, so notice that at any point of time, if I started with a beta distribution as my prior, my posterior will always be in a beta distribution form. It's just the alpha and beta values will be different. You understood, right? So now to basically, I've seen some number of examples, and I'm about to toss a coin, and you're asking whether it'll come heads or tails. Okay, then that depends. Answering that depends on is the probability of coming heads is theta equal to theta 1 or theta equal to theta 2 or theta equal to theta 3, etc. And for each of them, there is an actual probability. If it's theta equal to theta 1, then the probability of heads is theta 1. Okay, so I need to compute the expected value of that expression. Basically, I need to compute what's the probability heads given theta times p theta d theta, where p theta is my current posterior distribution on the theta. And if I do this distribution, if I do this integral, the nice thing is you'll find that for the beta distribution, the mean value for a beta distribution of alpha and beta is alpha by alpha plus beta. So if you have seen, you started with a beta of alpha beta beta distribution, and you saw h heads and t tails, your new posterior would be alpha plus h and beta plus t. Right? So your new prediction would be alpha plus h by alpha plus h plus beta plus t. So even though I dragged you through all these crazy looking integrals, in the end it's still just a ratio. If you were doing MLE, you would have just done, the number of heads by number of heads plus tails. Okay? So if you have just seen h heads and t tails, MLE would have said h by h plus t. If on the other hand, you are doing Bayesian with beta distribution with alpha beta as a prior, then after seeing h heads and t tails, you would say your prediction that the next one would be a head would be alpha plus h by alpha plus h plus beta plus t. Right? That's like adding a little to the numerator as well as the denominator. That's like imagining that you have seen more data than you have actually seen. So even before you saw the first toss, you acted as if you have already seen alpha heads and beta tails. And now you are seeing the next toss, and so it's like alpha plus h by alpha plus h plus beta plus t. So the net effect of doing Bayesian learning in this single example turns out to be just doing MLE and essentially adding virtual samples to the numerator and the denominator. So I can just say, to heck with the entire other stuff, I'll just do that. And if you do that, you would be doing what is called in the Laplace smoothing. Laplacian smoothing. And it's a nice place to end, because what we know as Bayes' rule has actually been made famous by Laplace, not by Bayes. Okay? And so in fact, he deserves all the credit for essentially Bayes' rule being known to the world. And this is called Laplacian smoothing, and it just sort of gets you directly to the end point, at least for this particular case. Okay? The next class, when we come back, we'll talk about Markov networks.